it's not the usual setting today, and therefore it's even more important to do an audio check. Can you please confirm whether you can hear me? So we don't have the usual setting today, and therefore it's even more important than at other moments to do an audio check. So can you please confirm in the chat whether you hear me sufficiently loud? I'll just keep talking to give you some volume to check your audio settings. So please confirm in the chat whether you can hear me, whether the audio quality is okay, because we don't use the normal setup today. And therefore I'm even more ignorant than on other days on how the audio quality will be. So please confirm in the chat whether or not you can hear me in the right way. Okay, I see that Leander says the audio is a bit low in volume. I can probably still increase that at my side. So this should be a bit better. I don't dare to exaggerate. Yeah, it is a different microphone and a microphone of a lower quality. So it must be different. I just hope it's good enough. By now it's 1 o'clock. So let's get started. So technical check, the video, yes, is working. The audio we have just checked, streaming must be on. Let me verify the recording light. Yes, that's on. And that means we can start. Today we have the feedback webinar on the chemical bond, which is quite a different topic than we had in the previous weeks. But before going to the science, as usual, let's go through some project-related and other practical things. The project, it seems all teams are going well. So you have submitted your convergence tests. I have given feedback on this in the past week. I think I have covered every team by now, but should I have forgotten somebody? If your team didn't get feedback yet, then let me know. Then I must have overlooked something. At this moment, I would like to give a few hints on how to handle these now probably somewhat larger calculations that you will need in the project. The most important hint I have given before, and that is still available on Zulip in the administrative news, that is how to enable parallel calculations. That is something you will really need for this project. So if you haven't tested that yet, look at how to do these parallel calculations. And now will follow a few other small but sometimes convenient things. For instance, if you have a calculation that has been stopped for some reason, oh, no, sorry, repeat. If you have stopped a calculation and you want to continue it, so starting a new calculation, maybe you have changed the position of an atom slightly, maybe you have adjusted the lattice parameters slightly, but you want to save time by starting from the output of a previous calculation. Well, if you still have um, the if you still have the files from that case, so the prefix should be the same prefix. If that is the case, if you didn't delete anything, then by specifying starting pot and starting WFC as file, just the word file, then it will read these saved files for the same prefix. And so your first iteration, rather than starting from free atoms, superposition of free atoms, your first iteration will directly start from the converged result of your previous calculation. So that can save some time. Usually, if you did only small changes, you will reach convergence faster. Self-consistency, I mean by convergence, you will reach self-consistency faster. A related trick, how can you interrupt a calculation? Say you want to uh, you want to use your laptop for something else. You could hibernate the virtual machine. That's definitely a possibility. But you can also really pause the calculation by this command, touch, then the prefix of your calculation dot exit. The touch command creates a file with that name and empty content, and if that file is there, when Quantum Espresso reaches the end of an iteration, it checks does that file exist or not. If that file exists, then it stops. And then later, if you use as restart mode restart, then you can just continue from that same point. So that is something you can use. If you would need to do magnetic calculations, how to do that? You have to set the n-spin variable to 2. The default is 1, but if you put it to 2, then it will allow a magnetic calculation. And you have to give for every atom that can be magnetic, that can have a magnetic moment, you have to give an initial magnetization. So if you put this for atom 1 to 1 and for atom 2 to 1, that means both atoms 1 and 2 have a magnetic moment that is maximally positive and they are pointing in the same direction. If you would put here 1 and minus 1, these moments would be pointing in opposite directions to create an antiferromagnetic configuration, for instance. And the results of a magnetic calculation that you will see in the output, you will have now magnetic moments for every atom. So in this example here with 5 different atoms, where 3 of them have a large moment in one direction, the fourth atom has a moment that is 10 times smaller and pointing in the opposite direction, and the fifth atom has basically no moment. So that will be the impact of a magnetic calculation on your output file. If you try large cases, sometimes it happens that your calculation stops with simply the message killed. If that happens, you probably try to use more RAM memory than your virtual machine can access, and that you can check by looking at the initial lines of the output file. You will find there something like this: estimated total dynamical RAM, and this number should be smaller than the amount of RAM memory that is allowed for your virtual machine. And how can you change that? If you go to the settings with the virtual machine not running, so here in this example, the virtual machine is running, then you can't change anything in the settings, you can only inspect them. If you want to change them, you have to first stop the virtual machine and then open the settings. In settings under system, there is the amount of memory, a slider for the amount of memory that your machine can use. So put it to the right hand side of the green area, and that is the maximal amount that is practically feasible. It depends on the hardware you have. A problem that appeared for one of you in the past week, sometimes the file system of the virtual machine can get corrupted by maybe filling the entire disk or by being interrupted when it was writing a file. So maybe you closed your laptop with the virtual machine still running, and that happened just when it was writing a file. So in that situation, it can happen that the file system is corrupt, and the next time you want to start the virtual machine, it will not do that anymore, and you get stuck with a window like this. If that happens, here is the recipe how to solve this. Give this comment, type this on that command line. When the system asks you then a question, rather than answering yes, answer an A, which means yes to this question and yes to every question that will follow. And once it terminates, then exit, and either it will reboot now automatically, or you have to restart the virtual machine manually. But in both cases, now it should get over this corruption message. That's it for the computational hints. Let me look at the chat. No, no specific questions on this. Let's then move on to the science, to the chemical bonds. So to build a table of contents of the course, we have spent quite some time to properties that depend on the total energy. We can predict the equilibrium geometry of a crystal. We can predict elastic properties like its bulk modulus. We can construct the entire phase diagram of which your crystal is part. All of this could be done based on the total energy. 2 weeks ago, we made an addition to that. We said, well, if you have the band structure and the density of states, you can describe other properties of your crystal. You can tell whether it is a metal or an insulator, which color it has, thanks to this electronic structure. That's a topic from condensed matter physics. Electronic structure is studied in condensed matter physics. So with that tool from condensed matter physics, you can make other predictions about the crystal. What you have done in the past week is something similar, but now starting from chemistry. We will use the language of chemistry to tell something about the electron density. The electron density is also something that can be calculated, and by understanding the electron density, we can have some insight in other properties of the crystal. So now it's chemistry that is leading us. And therefore, we started with the very basic knowledge about chemical bonding, the four classical types of bond, the covalent, ionic, metallic, and van der Waals bond, as it is described in textbooks, and most of you were very familiar with that as expected. This can raise a few questions every now and then. So somebody asked, why is a crystal with a covalent bond brittle? And why is that more brittle than say an ionic or a metallic bond? The facts, and maybe I should go back to that picture here because that picture happens to be the visualization of a covalent bond. You see anisotropy here. There are directions in which there are electrons accumulating. There are directions in which the bond has different properties than in other directions. So this is an anisotropic bond. And if you have something anisotropic, then brittleness will be a possibility. If something is isotropic, then depending in which way you try to deform a crystal, well, every way is the same way. Every direction is equivalent to another direction. But if you have directionality and isotropy in the bonding, then not all directions are equal anymore. And that is one of the ways how brittleness can set in. There can be specific directions. If you try to deform the crystal along these directions, then it will either be stronger or weaker than along other directions. That is brittleness at the level of single atoms, at the level of bonds in a perfect crystal. There is also brittleness at the level of the microstructure, so not at the level of a unit cell of a perfect crystal, but rather at the atomic scale in a realistic crystal, where you could have, for instance, and I have here the example of a simple cubic lattice, with here half of a plane extra that is inserted. So if this plane here, this half plane would be missing, you would have a perfect cubic crystal lattice, but you have squeezed in half a plane here. That is a defect, a dislocation, a defect that often appears in crystals. And if you now try to shear this crystal, well, what will happen is you will push this extra plane closer to this regular plane here, so close that here the bonds may break and that this plane can take this position, and this plane, half of this plane, becomes the new one that is inserted here. So by shearing the crystal, by uh, pulling at the top and the bottom in opposite directions, you have moved that dislocation one unit cell to the right. And if you keep shearing, if that dislocation keeps moving, in the end the half plane has moved through the entire crystal. Well, the ease by which dislocations can move, that is a very strong determinator of brittleness. If dislocations move easily, then your crystal is ductile, not brittle. If dislocations are hard to move, then you will have a brittle crystal. But that is something decided here at the microstructure level, not at the level of one unit cell. And these two effects, anisotropy in the unit cell and ability of dislocations to move, they can cooperate or they can fight against each other, and that gives rise to all the different elastic properties of crystals. After this textbook examination, we moved to the concept of cohesive energy. and you are confident to define what a cohesive energy is, the energy difference between free atoms and the crystal. And as introduction to that topic, I asked you this at first sight, perhaps a bit of an off-topic question about free sodium atoms and free chlorine atoms that combine to a tablespoon of salt and that release heat in that process. And I ask how much has the temperature of the room increased. Several of you commented that this was not an easy question to answer and also not a nice question to answer, and they did not see the connection between this question and the real topic of this module. And I agree that the question is a bit out of the normal, but I keep it there because it plays a specific role. What do I want to achieve with this exercise? I want to let you feel that cohesive energy, which we calculate here from DFT, which arises for us as a quantum property, something we need quantum physics to calculate it. Well, but cohesive energy is not just a quantum thing, it's a realistic property that you could observe in nature. If you would be able to mix free atoms to make salt, then you can heat your room by this. It is something that appears in traditional chemistry. So, and by construction, the question that was asked there, although it is a bit far-fetched with these free atoms, but the way how the question was formulated was a kind of chemistry question exercise that you could find in a basic chemistry textbook. So to show you cohesive energy, yes, we calculate it from quantum physics, but it is a property that matters in chemistry in general. And that was the secondary message of this exercise, it gives you a feeling to the size of this cohesive energy. It's not a tiny thing, because we saw you can heat your room considerably by by creating that tablespoon of salt. I have collected here all the answers you have given, and some people found that the temperature rise was very, very small, but most people found something in the range of 1 to a few degrees Kelvin. And there is quite a spread on these numbers because it depends on how large do you estimate that the room is. So in the standard solution that was provided, it was about 2.5 degrees uh, by which the temperature of the room was increased. So all of that due to the energy released by the cohesive energy. So that's not a small thing. And if you want to see the entire reasoning, then when you had uploaded your answer, you could download a PDF file with the complete description. Some people keep doubting about the difference between this cohesive energy that we met for the first time in the module of the past week and the formation energy that we used 2 weeks ago or 3 weeks ago when we constructed phase diagrams. So these are similar quantities, but not identical quantities. And what is the difference? The cohesive energy, that's the energy difference between a solid, a crystal, and the free atoms of which that crystal is made. Cohesive energy. Whereas the formation energy, that is the energy difference between, again, that same crystal and then the elements of which the crystal is made, but not as free atoms, but as unary substances. So solid sodium, which is a crystal itself, and chlorine molecules, which is a gas. So you take the elements in their ground states, either gas or crystal, and now you consider the energy difference with the binary crystal you want to make. That is the formation energy. And in this you see that a formation energy will always be smaller than a cohesive energy, because you need, if you start from the free atoms, yeah, they would be somewhere high up here in an energy scale, and then you make these unary crystals or gases out of it. Well, you already release cohesive energy here, and now still a little part is left to be released to make the binary crystal. So formation energy is always a smaller number than the cohesive energy. We will use this cohesive energy, which we can calculate, that will become a number. We will use this cohesive energy and the visual information that is hidden in the charge density difference in order to tell from DFT what are the chemical bonds that we have in a given crystal. And therefore we need to know how to calculate cohesive energy by a DFT code. And that gives some issues for a few people, mainly about how to calculate the energy of a free atom with DFT. And this was something, well, I didn't explain that. I just provided everything you needed. We have files that were indicated as, yeah, these are single atom files. So for the aluminum crystal, you get a pseudopotential and an input file for quantum espresso. And if you would look at that input file, then you would see that it has this unit cell, which looks like a primitive FCC unit cell. So that's strange. This is an FCC unit cell, but this is for a free atom calculation. But if you then would measure the distances between the atoms, then the distance between these two aluminum atoms would be more than 10 angstroms, which means very far apart. This is an FCC unit cell with a lattice parameter that is very large, so large that the atoms effectively do not interact anymore with each other. So this is a trick to do a free atom calculation with a code that can only accept unit cells for crystals. So you have made an artificial FCC crystal with a very large lattice parameter, and therefore what you calculate are basically the properties of free atoms. This trick is called a supercell, and in 2 or 3 weeks we will have half of a module that is dedicated to that, because you can use supercells also for other purposes. So if you wonder how did we calculate, or how can we use this to calculate free atoms, and will we do something with free atoms later? So that was the answer. And yes, we will explicitly look at doing free atom calculations in a few weeks. You could also wonder, why do you have to do these free atom calculations in a spin polarized way as a magnetic calculation? That was explicitly instructed. And the reason is that many free atoms do have a magnetic moment. And if you would not allow for that magnetic moment to exist, you would not have the ground state of the free atom. And therefore, your cohesive energy would be wrong, because it's measured between the ground state of the free atom and the ground state of the crystal. You can imagine everything that is here in the group 1, where you have an s orbital that is filled by one electron. That's an unpaired electron. All these atoms, as free atoms, will have a magnetic moment. Same for everything from the d block. You start filling the d orbitals, but until you are at zinc at the end, at cadmium, at mercury, until you are at the end of the d block, you will have an incompletely filled d shell, so you will have a magnetic moment there. Same for the p block. There, only when you reach the noble gases, you have no moment anymore. So group 2 has no moment, group 12 has no moment, and group 18 has no moment, but everything else in principle has a magnetic moment as a free atom. In crystals, this is totally different when forming the crystal. For most elements, except for, say, chromium, manganese, iron, cobalt, nickel, and these 5 3D elements, apart from mainly these 5 elements, everywhere else magnetic moments disappear if you make a crystal out of these atoms. Now, having seen these input files, we can calculate for these 4 crystals their total energy as a crystal, here expressed per cell, here expressed here expressed per cell, yeah. And here we have the total energy for these 4 atoms, 5 atoms as free atoms. And now we can make the differences, and that can give us the cohesive energy, here expressed in electron volt per formula unit, but easier to express it in electron volt per atom, because now you have a quantity that does not depend on how many atoms are there in one formula unit. And you can readily see from this that if there is a van der Waals bond, yeah, that's a very weak bond, your cohesive energy will be much smaller than for the other 3 types of bonds. So this is a way how to isolate the van der Waals bonding from everything else. You could wonder, if I do this cohesive energy calculation, do I need to do a geometry optimization of my crystal before, or can I do this with, well, a rough estimation of the geometry? Look at these numbers. They are several electron volts in size. So, say 3 to 4 electron volts between the 3 large strong bonds compared to the van der Waals bond, 3 to 4 electron volts. And what was the impact of geometry optimization? In our iron aluminum example, this had an impact of 0.1 to 0.2 electron volt per atom. So on the same scale, electron volt per atom, geometry optimization 0.1, 0.2, whereas the values for the cohesive energy are 3 to 4 electron volts. That's an order of magnitude difference. And that tells you, if your only goal is to isolate van der Waals bonding from the rest, then geometry optimization is not needed. You will reach the same conclusions with or without geometry optimization. If, on the other hand, you want to have a cohesive energy that is as precise as possible for whatever reason, yeah, then you must do geometry optimization. So it depends on your purpose. Then, with the charge density difference, there we can distinguish between the 3 other types of bonds, and that were the pictures you have seen. If you have the electron accumulation here in purple evenly in between the atoms, then we have a metallic bond. If you have localization of the electron density maxima in between atoms, then we have a covalent bond. And if you have localization of electrons on top of atoms themselves, so not in between atoms, but in the area where an atom appears, then we have an ionic bond. Of course, there can be many complications when you have crystals with mixed types of bonding. So not every time the picture will be that clear cut because the chemical bond does not really exist. We make this classification in four, but this is a continuum and often you will doubt, but for the clear-cut cases, this definitely helps. A very practical problem that could arise if you were looking at these pictures, that is that sometimes the pop-up windows appear outside the visible part of the screen if your resolution of the virtual machine is not set correctly, and therefore if you had that issue in virtual in the Quantum Mobile, you can take the settings of Quantum Mobile, go to Displays and change the resolution. You have many possibilities there. Not all of them will work on your laptop, but if the screen was too large to display everything, you can make it smaller or the other way around. Somebody wondered here, well, for this charge density difference, we need to subtract the free atom density from the crystalline density. But we haven't done free atom calculations here. So how is that possible? And that is because when you follow this methodology for a charge density difference calculation, then this instructs Quantum Espresso to do these free atom calculations internally, not via supercells, but really via an isolated atom in empty space. There is a different non-periodic formalism that can be used for that purpose. So with this, I hope you understand how to use DFT to examine the chemical bonds in a given crystal. And for most people, that turns out to be understood. We used that insight to look at what I called an old puzzle. How is the ionic bond in the prototype ionic crystal rock salt? How is that described? And therefore, to prepare for this exercise, I had asked you several weeks ago, out of the blue, how you would visualize an ionic bond. And these are some of the pictures you submitted. And you have the pictures where you have a completely filled orbital for sodium because you have removed one electron and you have put that electron here at the empty spot in the chlorine orbital. And some of the pictures even explicitly draw this arrow, suggesting that the electron transfers from one atom to the other. Also in this picture, you do have the arrow. And that gives then rise to positive sodium ions and negative chlorine ions that Coulomb attract each other and these arrange themselves in this rock salt crystal. That's the idea of an ionic bond. But then you saw we can confront this with DFT and we see that there is more charge in the chlorine atom and more charge in the sodium atom, rather than less charge in the sodium atom and more in the chlorine atom. So the idea of a jump of an electron going from one atom to the other is not confirmed by our analysis in in on the density as calculated by DFT. And the reason for this, as was explained, is that this idea of an electron that jumps is simply not right. You have the sodium atom with its unpaired electron at some typical distance, and that typical distance turns out to be the bonding distance between sodium and chlorine. So by just sitting next to each other in such a way that the sodium electron is at the position of the chlorine atom, yeah, there the bond is made. So no arrow, no jump. That was the message here. That was related to the concept of crystal orbitals. So in a crystal, the electrons are moving in crystal orbitals, just as they are moving in atomic orbitals in an atom, or in molecular orbitals in a molecule. So the crystalline orbital is an extension of that same concept. And I showed you pictures of that, yeah, like here pictures where you could see, so the areas here throughout space, these are isosurfaces of crystal orbitals. So you could imagine them as, yeah, in a cartoon, as these types of objects, in contrast to the orbitals of free atoms, or the inner orbitals in an atom. So the 1s orbital is very localized around the nucleus, whereas the 3s orbitals are delocalized through the entire crystal. And after having seen this picture, there were people who wondered, how can we make such a plot? Well, you can't, because these plots were made with XCRISDEN and a different DFT code, who have both the rare compatibility that such plots are uh, routinely possible. In quantum espresso, as far as I know, this possibility is not there. So it's not something you can out of the box plot yourself, although if you would really need it, I don't think it will be too hard to find a DFT code that could do that for you. So, but here it was more about understanding the concept of a crystal orbital rather than about being able to plot one yourself. It's also not the type of picture you will often see in papers, but it's a nice image to think about. Good, that brings us to the end of the science for today. Let's have a quick preview on next week. So next week, yeah, we had already something from condensed matter physics. We had already a topic from chemistry. Next week will be a topic that is more typical for materials engineering. We will talk about elastic properties of crystals and about how to calculate these from DFT. You know the drill by now. I give you 5 minutes to write your summary of the past week and to formulate an exam question. And after that, I will have a last look at the chat, where so far no further questions appeared. So, but in 5 minutes, we will look again. Okay, then let's look at the chat. I don't see anything new, so good. We can stop here and we will see each other normally again next week. I'm not yet sure whether I will be able to do that as a live broadcasting. It can be that it will be pre-recorded earlier in the day, but in any case, it will then play automatically on YouTube and it will be available in the core site as well. If I can do it live, I will do it, but I cannot yet guarantee that. Okay, so see you next week.